Are we cool, Nico?
Yes.
All right. It's my great pleasure to welcome Nicolas Libedinsky from Universidad de Chile, who will be talking about the categorification learning seminar.
Okay, thank you very much, Ben. So thank you very much, Ben and Nicole and Michael and all the organizers for inviting me here. I decided to do a talk in GoodNotes. It's more like an artisan, more than I don't know. So this talk is called on Kazhdan-Lusztig theory for affine Weyl groups, which is like a huge title for what I will explain, and it's partially in work with Leo Patimo, and like the theorems are with Leo Patimo, and the work in progress is with Leo Patimo and David Plaza. So let us start with the beginning. When I wrote the abstract and the title, we were in a very different situation that we are now. We had like the most important breakthrough. We had it like last week, 1 week ago. So it will be very, very tentative what I will explain. It's not fully proved, but it's like, I like it very much. So let's go. So let's start with the definition of the Hecke algebra. So the Hecke algebra H of a Coxeter system, WS, is a ZV-V-1 algebra with generators HS for S in S and relations HS squared equal to V-1 minus V HS plus 1. This is the quadratic relation and the braid relation, where here the MSR is the numbers defining the Coxeter system. And so you know that when you write an element X in W as a product of elements in S, of simple reflections, you define HHX as so. And this is a lemma, a theorem that this is well defined, so it doesn't depend on the reduced expression that you chose. So these guys here, they are called the standard basis, and it's a basis of the Hecke algebra as a ZV-V-1 module. Then we jump to Kazhdan-Lusztig theory. So there is a ring morphism from H to H that can be defined sending V to V-1 and HX to HX-1 to the power of -1. So this determines a ring morphism. It's a duality. And so the big foundational theorem of Kazhdan-Lusztig in the 79 is that for every element X in W, there is a unique element Bx that they call C prime X in H in the Hecke algebra, such that it is self-dual, and you can write it in this form. So the standard basis is a basis, so you can always write it as a linear combination of HY's. But the whole point is you can write it with a linear combination where you have a 1 here, and the guys that appear here are in VZV. And this is the definition of the Kazhdan-Lusztig basis. And well, as the name says it, this is a basis. The Bx is again a ZV-1 basis of the Hecke algebra. And if one writes, so this decomposition, again, with polynomials, we have that these guys here are the Kazhdan-Lusztig polynomials. So the Kazhdan-Lusztig polynomials are the polynomials of change basis between the canonical basis or the Kazhdan-Lusztig basis and the standard basis. So one would like to understand what these polynomials are, and one could ask ourselves for what infinite groups you can calculate all the Kazhdan-Lusztig polynomials. And until last year, we only knew the infinite dihedral group. So the group generated by S and R with relations S squared equal to R squared equal to the identity and no other relations. So the affine value group of type A1 tilde. And this was known immediately. This is quite very easy to calculate, and the polynomials are essentially, what did I do? The polynomials are this. If y is less than x, and 0 if not. So it's very easy in this case, the infinite dihedral group. But other from that, there were no really infinite groups that were known. You can calculate finite groups, like by a computer, like Kazhdan-Lusztig. You can define it like this, but there is also an algorithm that you can calculate Kazhdan-Lusztig polynomials algorithmically, but it's like very slow. Anyways, you can calculate little groups. But for infinite groups, there was nothing known. But so Geordie Williamson, I think the year after his thesis, he sat down for like 3 months or more months, and he was able to calculate them. But so we were interested in this thing for other reasons. But he gave us these results with no proofs, and so we with Leonardo Patimo, we proved it. And so I want to show you what this thing looks like. So we are in A2 tilde, and we will call so this is the Dinking diagram, and we will call this reflection this is S1, this is S2, and this is S3. This is the blue will be S3. So, for example, here I define the elements xn, that is 1, that is red, red, green, blue is 1, 2, 3. And then I look at this modulo 3. So xn is just 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. This is xn. The theta are here I write a reduced expression for the thetas. This will be the elements that are associated to the fundamental weights. So theta 0, 0 will be, this is the 0, 0, 0 times the first fundamental weight. These are the fundamental weights. And so 0, 0 is this, 1, 0 is this, 2, 0, 2, 1. And so we associate the value group element, the affine value group element, so that it's related to that. So you just, so that's why you construct the thetas. So theta 2, 2. I hope it's clear. How do you define the thetas? Maybe I will get closer for you to see better. So this is theta 0, 0, theta 0, 1, theta 1, 0, 0, 2, 1, 1, 2, 0, 0, 3, 1, 2, 2, 1, 3, 0, etc. Then here we have the, but I chose this reduced expression for the end of the talk. Like, just, you have to know that there is this fixed reduced expression, that it will be my favorite reduced expression. That is essentially going like that and then like that. And then you have the definition of the Zn. These are the Zn. These are Z5, Z6, Z7, like that. And well, Z prime n, whatever. So For x in W, we define the n of x as this sum. So it's essentially adding all the guys that are less than x. You have all the hy for y less than x with a little correction. And so we have the theorem, as I said, based on an unpublished work by Geordie Williamson this year, that says that the canonical basis in the wall, so the wall will be this. And the thetas will be this. So you have, in the wall, you have, this is the decomposition. If n is odd, you have that the Kazhdan-Lusztig basis on xn is nxn plus v n xn minus 3. And if n is even, you have the same plus two correction terms in terms of the standard basis. And the canonical basis, maybe here I should say in the thetas, is just the canonical basis in theta mn is just the sum of v to the power 2i of n theta m minus I, n minus I. So it's extremely simple, that's the point. It's like amazingly simple. And then you could ask yourself, like, why is this giving you all? Well, essentially, like this, you can all people here and here and here are like kind of like the same. You obtain rotating the linking diagram from these guys, so they behave essentially the same way. And here we have the last part of the theorem. That is, if S is S0 and T is S2m minus 2, so you will have these formulas. So the BS theta will be the BS B theta. The B theta T will be B theta BT. And BS T theta, it will be BS B theta BT. And with this thing, and what do I mean with that? When I mean, like, I have the BS, the B theta, and this is, this guy here is BS theta, or theta T, no, theta T. This would be, maybe I should switch. This would be theta, oh. Theta 11 T. And so with this, you obtain this formula for that element. You obtain by reflecting here. You reflect here, and you obtain S theta. So reflecting here, this one goes 1, 2, 3, 1, 2, 3, 1. Sorry, 1, 2, 3, 1, 2, 3. You go here. This would be S theta, and this would be ST theta. So essentially, you will obtain with these things all this, what we call beyond the walls, or everything that is not everything that is not in the walls. So this is like this, and the walls is this. Oh, what did I do? These are the walls. And so we gave the definition there of all the Kazhdan-Lusztig bases here and here in these two regions. But the other regions, like for example, this region here is just rotating this region. And so essentially, this this region, and this region are essentially the same modular changing 1 by 2 and 2 by 3 and 3 by 1. And these other 3 regions are like, you see that they are kind of different, but they are equal between them. It's the same again, the same reasoning. So, voila, the theorem. And so it's so like, one point that we see here is that it's really easy, like it's beautiful. And on the other side, it's a question like how can you see that this is like just a sum of ends. Is this a general fact? And so the thing is that it's more general. So we want to do the same for AL tilde, for L bigger than 2. So we have to divide this in 3 big parts. So the first one is to find formulas for when you write the Kazhdan-Lusztig polynomial of some theta. So theta of lambda would be a dominant weight, and you associate so theta of lambda will be the affine Weyl group associated to that. And you want to write this as a sum of this. And as a matter of fact, the fact that this is in N, it's true in AN tilde. And it's not true, for example, in D2 tilde. But it's like a crazy thing. This is called the atomic decomposition. To write the Kazhdan-Lusztig basis of the theta in terms of the theta in terms of the n. And so the atomic decomposition it was in 2018. It was proved that it is positive in type A. And in type D2 tilde, it's not true, but apparently when you raise your rank, it starts being true. So it's quite strange, the thing, because like apparently it's, well, I don't know, but it seems to be true that this is a positive decomposition in higher ranks in any affine Weyl group. Then the second big step is to find formulas for Bx in the big regions. So the big regions here are these things that I showed here. So essentially everything that is not in the walls. These are the big regions that you can define them as the lowest two-sided cell in the cell order. So the two-sided cell that has the biggest A function, or the two-sided cell that contains W0. And the third part, and it's really interesting and difficult, is to find formula for Bx with X in the walls. So the walls is everything else, like here would be this. So, well, that's our goals. But these are like old things, essentially. Like many people have thought about some of this stuff. So the first question, for the first question, there is a long history. So essentially, if you have lambda and mu, two dominant weights, you have that the dimension of the simple highest weight representation of the complex semisimple algebra of weight mu lambda, it's the Kazhdan-Lusztig polynomial of lambda mu evaluated in 1. So understanding these Kazhdan-Lusztig polynomials evaluated in 1 is equivalent to find character formulas. And like character formulas, there's a lot of them. So I think that everybody knows the Weyl character formula, that it's a beautiful formula general formula, but it's difficult to calculate with it. It's useful to prove stuff, but it's not so easy to calculate because it essentially gives you like a lot of systems and you have to solve them. And when it's big, it's essentially impossible. Then you have Freudenthal's formula, that it's a recursive formula. I mean formulas for this. Freudenthal formula, that is a recursive formula, and it's usually what they use in if you want to program stuff. This is like the formula you probably want to use. Then you have constant multiplicity formula, that is, I think that it's a super beautiful formula with a plus and minus, and using constant partition function, that it's like extremely simple to define, but kind of hard to, I think that it's not so easy to calculate with this. Then you have more recently Littleman paths that give you positive formulas for it. And all of these, they are for any affine Weyl group. And then Littleman paths is like, so you obtain this as a sum over the endpoints of some paths that are acted on by some operators. Then you have Sahi's formula, that it's a formula coming from Cherednik algebras. And it's also a positive formula, but it's a sum of rationals. So you obtain this as a big sum of rational numbers. Mirkovich-Vilonen cycles, that it's, so essentially you have this relation between the intersection cohomology of some sub-variety of the affine Grassmannian. It's isomorphic to the simple highest weight module, and then these are cycles the cycles are sub-variety that intersect this in a basis. So well, this is a very rich thing. And there is a Q analog of these guys. So in 1983, in a famous paper, Lustig defined the Q analog of these guys, and the Q analog is the Kazhdan-Lusztig polynomial, the full Kazhdan-Lusztig polynomial, not just evaluated in one. And he conjectured this formula of Kato, that it's an analogous formula as the constant multiplicity formula, but with a Q. And then Lascaux, Leclerc, Thibon, they proved a positive formula for this Q analog of the weight multiplicities using Kashiwara crystals of the quantum group. So we are in a categorification seminar. So this is like usually very long and difficult to, like, you need maybe 20 minutes to define these guys. But there is a category that is the diagrammatic category that some people call Elias-Williamson category, or just the diagrammatic category. That it's, Mikhail Khovanov here also did a huge job in defining this, because he defined it with Ben Elias for the symmetric group, and then Ben did it for the dihedral groups, and then finally Geordie and Ben did it for every Coxeter group. And so they have this that I put a 0 because there is a field that you have to define it over a field, or even over more general rings, but let's say a field. And so you have that the Grothendieck ring of this monoidal category is isomorphic to the Hecke algebra. And if you take the indecomposable objects, they go to the Kazhdan-Lusztig basis. Maybe I should say that this is a theorem by in full generality. This is a theorem for every Coxeter group. This is a theorem by Geordie Williamson and Ben Elias. Their Hodge theory paper, and there is also like this category is it's very easy. It's like you just change the base field and you define the same category, but over a field of characteristic P. And then I'm skipping here the details, but this is like the essence. So you have that the decategorification of this is still the Hecke algebra, and you have that the indecomposable objects go to some guys that are the p-canonical, called the p-canonical basis. So it's a basis that depends on p for a prime number. And when you write the p-canonical basis in terms of the standard basis, you obtain the p-Kazhdan-Lusztig polynomials, and they control the simple and the indecomposable tilting modules of the reductive algebraic group associated to this. So this is, of course, all what I'm saying. In fact, even this, all of these results are extremely hard and important and stuff like that. I'm not stretching that enough, but this is like the proof of this is very complicated, and many people participated, like Simon Rich, Pramod Ashar, Ben Elias, Ivan Lozev, Geordie Williamson, Maki Sumi, etc. Many people with beautiful and complicated papers. But essentially, the thing is that the p-Kazhdan-Lusztig polynomials are like, if you understand them, it would be amazing, because it's like understanding the characters of the most important objects. And so I will just I will just write an inspiration. So the p-canonical basis is really not something that we know how to calculate. I mean, you can calculate here the p-canonical basis. There are algorithms to calculate the indecomposable objects, but there are algorithms in a category. You have to do like calculate all these kind of morphisms and then compose them with other morphisms and then see the rank of some matrix that appears. And so it's like a very complicated process. So the question would be like, how can you calculate this in an easier way? So they are known in A1 tilde, the p-canonical basis, but already in A2 tilde, they are not known. And there is a conjecture by Lustig and Williamson that it's for what they call the second generation elements. So I will just write I will just give maybe I should say Lustig's Williamson generational philosophy. It's like you define for a dominant weight a sequence of characters, such that the first one is the character of the simple module of the Lie algebra. So you can calculate it. This is given by the Weyl character formula, for example. The second one is the character of the simple associated to the quantum root at pth root of unity. So the first ones, they mean stuff. They are characters of some simple modules in some category. Then you have that you pass from xn to xn plus 1 by some kind of formula involving Kazhdan-Lusztig polynomials. And then at some point, it stabilizes. And you have that the end part is the character of the L lambda that I wrote here of the reductive algebraic group in positive characteristic. So essentially, this philosophy that they take to try to understand the p-canonical basis is try to divide the problem and approximate successively. You want to approximate successively the character at the end, the character that you're searching for. You start with something easy, and you make it more and more complex until at some point it stabilizes with your p. So you fix p and you fix lambda, and at some point it will stabilize. So this is just inspiration for us. So we knew that in AN tilde, it's an open problem to write down the so what I explained before, if you want to write down the canonical basis in terms of the ends, of the end of y, this is unknown what you have to obtain. And we were like trying to solve this for like many months with Leo and David. We have been staring at data for months, and there are so many beautiful things that happen. So we were always feeling that we could find something. And at the end, it's like some kind of thing that it's kind of similar to this philosophy. Essentially, you define, you interpolate. So you start with, you fix your lambda, dominant weight, and you will define n lambda I for I in between 0 and L plus 1, such that the n0 is just the standard basis, and the last one is the canonical basis. And you want in the middle to approximate the Kazhdan-Lusztig basis. And so we have a precise definition of the n lambda I. This is something that we know how to define. In fact, we know how to define it in any affine Weyl group. We just don't know. This, as I explained, this is like a really last week thing. So I'm extremely excited about this because it's like the breakthrough we have been waiting for many, many months. And you can calculate explicitly the n1. It's also is just the sum over xy of this kind of standard basis. The n2. This is a theorem now. We proved it yesterday. Is that the n2 is the n as I defined before. The n, recall that it's like the sum of the standard basis for everyone that is less than theta with some correction, with some coefficients. And so now we can prove this, that n2 is this. So this is true, this is true, this is true, this is true. We know this. These two in general are still conjectural. We know how to prove this in A3 tilde and probably in A4 tilde. And what is this? Is that to pass from ni plus 1 to ni, it's essentially super easy. It's just monomials. You have some monomials and we control completely the guys that appear here. So it's just like the best situation you could imagine. And the only complicated part that apparently appears is when you pass from n3 to n2. Then you have some kind of deformed constant partition function. Something also very, very concrete. So if we are able to prove this, like I think that the level of computations of this will be like immense. We will be able to calculate way further, and I think that conceptually it's really, really nice. Like, and I dream with some kind of like relation between these two kind of I don't know, approximations, like the p approximation and this approximation. That is kind of like a characteristic zero approximation. You start with the standard basis and you finish, and you get closer and closer to the Kazhdan-Lusztig basis. This in here, you don't see, well, you see that essentially when you divide the problem, passing from Kazhdan-Lusztig to the n polynomials, dividing the problem in Kazhdan-Lusztig going to n and then to the Kazhdan-Lusztig polynomials, this gives you, and you see that it's an extremely simple thing. And this is apparently, the generalization of this is not to consider the n directly, is to consider this filtration. And to finish, I thought I was not going to get here, but apparently I spoke too quickly. Sorry, I didn't say that this is work. This is work in progress with Leonardo Patimo and David Plaza. And so I said also that we would like to, another dream that I have, that it's also like kind of like a not long-term, a middle-term project that it would be a dream for me is to try to, so the p-canonical basis is different from the canonical basis. But how different it is something that I would like to control. So in what sense precisely, I would like to say that what are the bad essentially what are the bad primes in Lustig conjecture? The primes, and so I would like to say the bad primes in Lustig conjecture are the bad primes in type AN. I'm only thinking in SLN. So the bad primes, I would like to say they are the bad primes in AN that I don't know what they are, plus something that is controllable. I would like to control, to say exactly what are the other primes. That is like my middle term dream. I don't know if it's doable. It seems very complicated. So in A2 tilde, we have a theorem also in the same paper with Leo Patimo, where we find, and for the people who don't know circle bimodules or the diagrammatic category, essentially each of these things are morphisms. And when I write this is the projector into the indecomposable of theta m plus 1 n. And this is, for example, the identity. So we have an explicit formula that it's based using the geometric Satake and a conjecture by Ben Elias that he calls the clasp conjectures. We kind of were inspired in these things to prove this. This is a theorem. And essentially you see what are the bad primes here. The guys are the denominators. And so it would be desirable to have the same kind of formulas for the whole, well, everything that is not AN, essentially, that it's in the P-restricted weights that are the one that control Lustig conjecture. So we would like to find similar formulas in the relevant cases. And in the big regions, with David and Leonardo Patimo, using geometric Satake and combinatorics a la Dyer, we are able to calculate recursively Bx for x in the big region for AL tilde with L less or equal than 7. So this torsion thing apparently is like, it's complicating our lives. But so in the third step, in the walls, we don't have really, so to give a summary, we have nothing. We have proved nothing. But we are close to understanding very well the thetas. Until A7 tilde, we know all the big regions, all the Kazhdan-Lusztig bases in the big regions. And everyone that is on a wall, it's just one step away from a big region. So this should, like, once we know precisely all the Kazhdan-Lusztig bases in the big regions, this might help us to find these guys in the wall. And if we are able to do that, well, that would be awesome to understand all Kazhdan-Lusztig polynomials in AL. I mean, it's awesome and extremely difficult. Like, it's really a long shot. Like, to understand the walls seems like the most complicated part. But the fact that we know the rest, the big regions, is like, I think that it will be really helpful because of several calculational reasons. And if we understand like these recursive formulas, at least for the Kazhdan-Lusztig polynomials, we will be able to do some analog of this for all the big regions, and hopefully for some parts of the walls, and then we will be able to control the bad primes in Lustig conjecture, modulo understanding the bad primes in in AN, which is probably the hardest problem. And that's all. Thank you.
This is good. We have a lot of time for questions, and I have a lot of questions. But please.
Oh, no.
Questions first. So I think Elijah asked a question, which I also wanted to ask. Just you're talking about bad primes in AN tilde versus bad primes in AN. And the bad primes in AN always show up in AN tilde because they control like the first thing that's happening down near the bottom. And then there's more, which you're saying will be understood if you understand these idempotent formulas.
I mean, the bad primes, they are in this p-restricted wave. They are all not all in AN.
What do you mean by a bad prime?
A prime where Lustig formula is not correct. Lustig character formula for the simple.
So can I ask you about this? Is there a relationship between this funny recursion with the ends and this description of the idempotent projecting to the theta?
Sorry, again?
I was trying to understand something you said. Is there a relationship between this recursive formula involving the generations of the ends? That's right.
Yeah.
So, and your description of the idempotent projecting to be.
No. This is like independent. The description of this should follow from. So in. I mean, this is kind of like. I mean, in the thetas. This kind of guys, the theta, the elements associated to positive combinations of fundamental weights, you should be able, I guess, to deduce this kind of formulas from your clasp conjecture. I mean, it's kind of equivalent. I mean, probably I think that clasp conjectures, it's. One can translate it into a conjecture of this in AN tilde, and then when you understand the big regions, you kind of understand more, like just more elements, more of these projectors. I mean, you want to have all the projectors. That would be like. You would like to have the projector for any element in the affine Weyl group, but like I'm just saying that the steps that I see as like the reasonable steps are like first proving this, the analog of this in AN tilde, then going to the big regions that have like kind of beautiful recursive formulas to, I mean recursive formulas to go from like here to go from here to here in this case. But in general, you have that the thetas are like 1 over n factorial appearing in the dominant part. So you need like there are lots of guys you need from each theta. You have to go to many directions to obtain all this, to fill up all these holes. And so I'm just saying that if you have these recursive formulas, you can obtain. Probably it will be kind of like not so complicated to go from these, say, generalized clasp formulas to a formula for these elements in the big regions.
Did you see Elijah's question in the chat?
No, let me see. Catarina, Elia. Yeah, essentially I'm saying that, yeah, I don't really know. I'm kind of like, that's what I would hope. Like I feel that the AN is the complicated part and the rest is kind of more accessible, maybe. But this is just like, like I'm sorry that I'm not really proving too much. This is really work in progress.
It still is interesting, but I'm just curious what you mean by the rest of it.
Well, I mean, like I mean that it feels like you start with like it's like a code, like the dimension of the space of the cells, of the two cells, seems to be like how easy they are to calculate. Like as you go, for example, in A3 tilde, you have like this, the big regions are this like these cones. These are 24 cones like this, and they should be like controllable, or they seem to be, they are controllable. And then the walls have like these lines that are different type of lines, like there are like triangular lines and square lines. And then the thing that is in the middle seems to be easier than the lines themselves. So it's like when you go down in dimension, it seems to be more complicated in terms of Kazhdan-Lusztig theory to calculate. So, yeah. But of course, like the real dream is to understand also, it's like if we are able to understand completely for all n, the big regions, then understand the codimension 2 parts of the walls, and then go down like that, then one could give like, one could understand everything, but that's maybe too ambitious, I don't know. But it would be great.
I'm really intrigued by this atomic decomposition, or rather the generational one. Do you have some idea about what the categorification of this atomic decomposition?
No, that's extremely interesting. I don't know. Like we just have this like at the level of Hecke algebra, and to prove this formula, we need because I didn't say what these guys are, but they are constructed. It's like a layer thing where you just consider the root, the roots that are the roots in A and tilde. They are sums of strings. Like it's like something like alpha 3 plus alpha 4 plus alpha 5, for example. And then in the n0 and 1, you consider in ni, you consider just things that are length ri or more. This kind of roots. And then you construct this n as a sum of Kazhdan-Lusztig bases where you just consider this kind of elements. I'm very imprecise, but it's very related to the length of the, if you say like alpha 1, alpha 3 plus alpha 4 plus alpha 5 plus alpha 6 is length 4 or height 4, it's related to the height, this I that appears. But I have no idea yet what this category is.
Like you're taking the moment graph description and trying to build the IC sheaf using like extending over various different edges and only some of them at a time. I don't know.
I don't know. I should think about it.
Do you have a similar description of these generations for things on the wall or things not weights?
No. No, this is just for weights.
Are there more questions for Nico? All right, let's thank him again. Silent clap.